Hi, I'm Akash.
I'm Isha. Welcome to No Math AI, the podcast where we break down AI concepts without any of the math. On today's episode, we will dive into generative AI for engineering design. Let's get started.
Today, I'm thrilled to have my dear friend, Professor Faez Ahmed from MIT Mackie. Faez leads the Decode Lab at MIT, and if you don't know, it's one of the leading labs that works at the intersection of generative AI and mechanical engineering. From thinking about how to create bicycles to how to optimally design airplane foils.
As we talked about in our last episode, we touched a little bit on how inference time scaling might actually bring the role of language models a little bit more closer to the precision it might need for engineering design. And there's no better person to talk about this than Professor Ahmed, whose lab has been working on this issue for more than 5 years. So everyone, welcome to No Math AI.
Thank you. Thanks for the welcome.
So let's dive right in. So can you tell us a little bit about this intersection between generative AI and engineering design? Large language models and generative AI as a whole has been making waves for almost the entire world nowadays. But how do we really bring the precision that we need for engineering design to the forefront?
So great question. In some sense, one thing is, what is engineering design? We all are surrounded by products, whether you are sitting in an airplane, you are driving your car, you're bicycling to a place, you're using your phone. All these products are created by designers. Yeah. And engineering design is the process of creating that product, right? Whether you come up with early stage ideas of what the next generation EV should look like, or you're doing a high fidelity simulation of really understanding the drag and getting that extra mile out of your charging. And in some sense, each stage of the design process has a lot of data. And sometimes it is about coming up with new ideas where generative models can give you, act as an ideation assistant, or it could be requiring really precise prediction or precise automation of the process. And these are the places where I see that generative AI has a huge role to play in engineering design.
Right, so this is about combining things and tools that engineers have always used.
Yeah.
And now adding a flavor of creativity with the help of generative models on top.
Yeah, and the fascinating thing for me is that why generative AI, right? Why should we just care about this new tool on the block, and why should engineers care about it? And to me, the first thing is it's effectively a word model, a lot of the knowledge that is captured in the word, instead of narrow AI models, which have been used a lot in the engineering domains. You are creating surrogates and so on. These models have a broader understanding and can capture much more complex distributions that were not possible before. The second thing, which you just alluded to, is can we actually go out of distribution? And out of distribution, going out of distribution in engineering is easy. If I'm designing an aircraft, let's say the wing of an airplane, and I say it should be a block, it's a very out of distribution solution, very useless, right? So how can we actually come up with out of distribution which is useful? And that's where in engineering, we care a lot about performance and constraints. Combining performance and constraints with novelty, creativity, and multimodality is where a lot of value can be provided for engineering applications.
That's a great answer, because I think that kind of leads us to our second question. So language models, or any kind of generative models, right? They're probabilistic.
Yeah.
Which sort of implies there's some kind of randomness built into this.
Yeah.
So how can something that is random help you design something that requires very high degree of precision?
Yeah, so this is kind of the key issue and the key thing that we think a lot about, because any generative model is learning a distribution. If we are asking for precision, which historically in engineering, a lot of optimization and design optimization is used, which gives you one answer, right? So why would you try to marry those tools? And the key thing here is that distributions mean diversity. And in engineering, it's very valuable often to get diversity. If I give you a car design, and maybe I give you one car design, that is useful sometimes. But if I give you a bunch of options, which are diverse, which are different from each other, but are all functional, then it provides you a lot more value in the decision making. And also maybe there are other factors that are not captured by the computational process. And as a designer or a decision maker, you can consider those factors and pick those options. This is where the value really gets highlighted. The other thing is, if generative models are amazing at, in some sense, enhancing optimization. Like we recently had a work around generative optimization. And when I hear about things like inference time scaling, I see that as one of the subtasks of generative optimization.
Absolutely.
Is how can generative models and optimization work together to get the best of both worlds.
And I think that is a particular topic that is of a lot of interest to Isha and me. In this work, specifically, I think you describe 3 different ways in which generative models and sort of the classical tools, optimizers, verifiers, can sort of work more collaboratively instead of sort of, the paradigm that we have been seeing with generative models coming into a field and like replacing tools that people have built, for years. You want to sort of expand a little bit on that?
Yeah. So when we think about generative optimization, effectively, like there are many ways to do it, and some of the ways that are there is maybe generative models that we have today, whether they're large language models, diffusion models, they're really good at getting you very close to the answer.
Yeah.
But the last mile is hard for them, right? And maybe we just, they can initialize an optimizer and then the optimizer can take over. And when I say optimizer, it could be a simulation tool, it could be your Monte Carlo search. There could be a lot of different ways to do a search or optimize. But that's one way, right?
So in this particular first case, what we're really optimizing is assume that my classical tool, the optimizer, is just expensive.
Yeah.
And so instead of wasting the time in the beginning, it's not so much waste, but to reduce the cost of running that optimizer, I'm going to give it a good starting point by using a world model, as you said earlier.
Yeah, exactly.
Okay.
And in some sense, like if you're doing, for example, high fidelity simulations of car design, right? If you start from scratch and each of your simulation takes like hours to days, and you have to do 200 iterations, that's non-trivial. And this is very common in engineering.
Right.
But if I ask a designer to say, like, give me a car and like close your eyes and just imagine a car, they would come up with a pretty good outline of a car that's aerodynamic, but they may not be optimal. So effectively, they are using the experience of cars that they have seen and coming up with a good enough answer. So same thing for generative models. We are getting very close to the solution. And then the optimizer can really optimize on like high fidelity aspects and so on.
This also speaks somewhat to this general question that people have when they discuss generative AI and how it interacts with, various players in the workforce, which is that there's a lot of fear in the knowledge worker vertical that a lot of the tools that we're seeing right now will replace, various types of knowledge workers. So what you're kind of speaking to here is that you see generative AI for engineering design as a collaborative tool with engineers and not necessarily as a replacement.
Definitely. I completely agree. I think that whenever these new tools come out, it's mostly to enhance the designers.
Yeah.
And it helps AI helps humans design better, right? And faster.
Yeah.
So on that note, what are the other 2 ways in which you have thought about mixing or combining or collaboratively using generative AI in the engineering workflow with the tools like optimizers and verifiers?
Yeah, so the first one is directly you are helping an optimizer. The second one is the optimizer is helping the generative model. So you're creating all your training data, or you are effectively, in one of our NeurIPS work where we were looking at aligning optimization trajectories with diffusion models, we said, what if the diffusion model's trajectory can be seen as the optimization trajectory? And the diffusion model training is learning from the experience the optimizer had. The third paradigm is also like maybe we are not just accelerating one or the other, we are helping with the problem formulation. And in this case, effectively, when people are writing down, they're given a problem, what are your design variables? How do you actually formulate the optimization problem? And this is also a place where the word knowledge plays a big role, right? What are the parameters that you should use? What are the design ranges that you should use? And once the problem is formulated, you can still solve it using classical methods or generative optimization techniques. There are lots of other things. I mean, they are in the paper. I'm happy to.
Yeah. No, I think when you were saying this, I was thinking about we know how to think about language models, performance in terms of some metrics that have become very popular. There's one out every day.
Benchmarks everywhere.
Exactly. Wanted to get a bit of your insight on when you think about a domain that requires so many considerations. I mean, multiple number of variables. Some of them, I mean, creativity. How do you even define that rigorously enough to then measure?
Yeah.
That's true. Yeah. So in some sense, this is engineering requires us to go beyond statistical similarity. And we have some work where we looked at this, where we said most of these generative models, by definition, are trained to mimic the training data. They are focusing on statistical similarity, which is like, how can I generate something very similar to what I've seen? Yeah. But in engineering, you need to do statistical similarity. So that is kind of still very core. But you care a lot about other things. Now, what are those other things? The first we talked about is performance and constraints. And what we have shown is that because in structural topology optimization, because most people were focusing on training models only on statistical similarity, a small change in a few pixels can make a big change in engineering performance.
Right.
So the model will make a lot of mistakes and will generate things that look similar, but they are not functional, right? So if you bring that metric during your training, it's useful.
So it's like having a bicycle where the saddle is levitating and
exactly, yeah,
that's off by like one grid of pixels.
And you don't want that design, right? Like things that are disconnected by a few pixels, they will not work in the real world. Similarly, you mentioned the diversity and novelty aspect. Like engineers care about getting a design that is different from the training data, but you don't want extremely different. You want different and functional. So that's one place where novelty plays a role. We care about the spread of the design space because we are effectively thinking about generative models being helpful to designers in design space exploration. Now, you want designs, getting designs all over the design space, but you also want the design space to be big, right? So uniformity and extent plays a role. Then there are metrics around like what is the human judgment? What are the other kind of factors that play a role in engineering? And all these metrics are important to get a holistic picture of when are these generative models really helpful for engineering problems.
Yeah. I think a lot of people, when they're thinking about how they're reading the latest language model paper and they're seeing, like Akash said, all the benchmarks that come out, you look at the graphs and you look at the tables and you're really impressed by, on this math data set of high school math problems, we did really well. But I think a common kind of a gripe with the world of language model research nowadays is that there is this massive gap between getting a certain number of math questions right and how you can actually use that to define metrics that are useful in real world problems like engineering.
Yeah, and it's both about metrics, but also about benchmarks. Yeah. So we had this interesting work with Autodesk Research where we created this design QA benchmark. What we did was we said, if the future is going to be where AI is going to help designers, what is one of the biggest frustrations for designers? It's taking that 150-page rule book and reading through that and saying, rule number 1.5.9 says that my wheel diameter cannot be between so and so. So we worked with the MIT Motorsports team and we got the rule book and we created a benchmark where we would effectively look at vision language models.
Yeah.
Where they are given some drawings of our MIT Motorsports team CAD models, and it looks at the drawing and we ask questions about, is this following the rules? Is it functional? And some questions are easier, like go find the rule number so and so. Almost for all other categories, state-of-the-art models, all of them, were very close to random.
Interesting.
That's fascinating.
So progress in the AI world and AI benchmarks is not very close to progress in the engineering world. Yeah. And this is just a very, very limited benchmark, but we need a lot more benchmarks to know when is AI having a real impact in engineering.
Yeah.
Where do you think, in terms of readiness, are today's best large language models? And let's include VLMs in them in terms of, I want to build some analogy here. So like, if you look at software engineering as a field of engineering, we've made great progress.
Yes.
where would you rank the readiness of these models for something like engineering design or mechanical engineering in general?
Yeah.
It's a bit hard to give a general answer for this, for the reason that design in itself is extremely broad. And I would rank for some tasks, the models are actually extremely good and very functional and can be used today. For some other tasks, things like requiring spatial reasoning and 3D word understanding and so on, or where there is not a lot of data on the internet, those applications, the models are not there yet. And there is a lot of research going on. There are a lot of startups coming up who are working on aspects of those problems. But I would definitely say that it's amazing to see how much progress we have made on AI for engineering design in the last 5 years. And I'm very excited about the potential.
So one particular tool that I want to get your insight on, Copilot did for people who work with code.
Yes.
And I know a lot of engineers and designers use different kind of CAD tools.
Yeah.
In fact, I was chatting with our CEO today who was telling me how he's using ChatGPT to help him design an enclosure for his switch, a fancy switch that he bought him. Tell us a bit about that. Tell us how language models are helping with the tools that designers and engineers have been using.
Yeah. So when we are thinking about tools that designers are using, CAD and simulations are some of the kind of major items. CAD is where there is a lot of research and startups that have come up in the last few years. Most of them, I think there is work around going from speech to some 3D model. There's work around going from image to 3D models. We have looked at GenCAD and GenCAD++, where you can scan an object and get a 3D object. And one thing that is important for engineering is that we don't want a non-editable version of 3D object. So a mesh and a point cloud, that's very nice and cute, but engineers can't edit them.
Yeah.
Right? They want a feature tree they can import in a software, and if they want to make any change, they can do that. So there is progress, and we have been researching this, and other people are also looking at it, that have seen that is happening in the CAD space. Having said that, the biggest bottleneck there is that some of the data sets that are out there are very limited. And the complexity of the data sets that are out there is not close to the complexity of what a professional engineer at Boeing or Airbus would be working with.
Right.
And this is one gap that we need to fix. And there are many solutions, synthetic data, create new data, other ideas that we are thinking about. So the other thing I'm excited about is engineering simulations. And in this case, there is this idea of we want to predict the entire flow field from engineering simulations. This is a non-trivial task because it takes hours to do that. And if we can learn that entire flow field, you can really design much better. And I feel like probabilistic surrogate models, which are generative models, learning from lots and lots of data is one way to go. In fact, we created a data set, DriveAirNet++, which was released in December this year. And we have had many companies approach us who are working, like car companies and software companies who are using that data to create foundation models and to create.
That's amazing.
And it's great to see so much interest in this topic, right? I think AI agents is something which is potentially going to have a huge role, because design is not just about one software. It is about different roles of people and different softwares.
Yeah.
So I can imagine AI agent which is using both CAD and simulations and taking the CAD model, simulating it and going back and seeing what the aesthetics could be and so on.
So as you mentioned this idea of agents in engineering design, everyone in the AI world is really excited about agents nowadays. And people who are really integrated into the engineering world know that doing your work on your own is one thing, but collaboration is one of the most important parts of the engineering design process. Can you touch a little bit more on this idea of agents and how you see the future of engineering design in that area?
In my mind, AI agents are going to have a huge role to play in engineering design. And to take a step back, if you look at the design process and you talk to anyone who works in the car industry, they have this, the middle part of the design process is called the devil's cycle. Because the early stage designer who sketches has no idea what the CAD guy will say.
Yeah.
And the CAD guy does not know what the simulation guys will say. And when there's feedback, they are like, oh, now what do I change to actually make all the constraints, right? In some sense, when I think about right now, we are developing AI models in silos, where we are creating a model which does CFD predictions well, or we are trying to create models which can do CAD well. But what agents enables us to do that is effectively, we just had a work where we showed a proof of concept, very early stage, where you had an aesthetic agent for car design, which looked at early stage design and said, okay, I can create some new kind of concepts based on control net and so on.
Yeah.
Then you can take the model and create CAD. You can create 3D geometries. You can send it to the meshing agent, and the meshing agent can create a mesh model, which can go to the CFD software. And that can actually like check if the mesh is good or not, and can you go back to the sketch and so on. So this whole idea, I feel like as we create better tools, AI agents can really weave them together for doing integrated designs. And also play different roles, because not everyone is a designer, right? Like some may be like judges of design. And completely different from this work, we had a different perspective where we said for early stage design, can the current vision language reasoning models be good judges of AI? Of design concepts. And what we looked at is we had a data set of early stage milk frother designs where students had created these sketches, and some from Penn State, they had expert raters rate each of those sketches by 2 experts. They also had trained novices.
Based on that design, 105 pages design book.
No, this was conceptual design. So they had sat down and rated like 1,000 sketches, right?
Oh, wow.
And then they also had trained novices who rated all of them. We gave these sketches with some prompting and so on for AI judges. And
with some basic design principles.
Some idea, context. What we found was that, and we came up with a statistical suite on how do you ensure that it's really expert equivalent. And we found that the latest reasoning models were better than 2 out of 3 AI novice judges who were trained by experts, and it was a huge cost thing. But they were also almost equivalent to one of the experts in rating, scalable rating for creativity and novelty and uniqueness and so on. So this is like, we are talking about different roles AI can play. In some places, you are just making predictions. You're creating CAD model. You're judging design ideas. And my hope is that in future, we can bring them all together.
Faez, this is something you always say. Your goal with generative AI is to democratize engineering for everybody.
Yes.
These 2 examples are really amazing. I mean, using agents collaboratively, to Isha's point, to solve real world problems, and then having reasoning models be used in a practical setting, unlike solving AME questions or Math 500. Just very fascinating.
Yeah, and I think as engineers, we care a lot about creating better designs faster. Most of the time, that's what we are creating. But I feel like one of the big value proposition for me, at least, is how can we democratize design? And people who can't write good poems or can't make very good art, today the generative AI enables them to do much better as close to experts, not near experts. And in design, you need not be trained in using specific engineering softwares to tap into your creative potential. Like a lot of people have good ideas, but they don't want to necessarily learn all this complex softwares. And what if we can have AI agents help them? Right. And they can still create better designs.
I love that answer.
I love this so much because I think it speaks to the potential of AI to be useful for all types of people and not just people in a certain sector. For those of us who are not car enthusiasts or who do not have a license to drive, do you have any kind of other applications you're excited about?
I'm lucky to have a group of students who are doing like work in a lot of different applications. And I feel like in our field also, people are looking at it from different perspectives. Some of them we are looking at like structural design, in general mobility solutions like bicycle, cars, aircraft, ship design, for instance, energy solutions like wind turbine designs. And there could be like other applications of systems design, and we've looked at linkage design and mechanical machine design and so on. So I see a lot of kind of like interesting work that is happening in the field.
That last one is like very dear to my heart. I do want to double click on. I think it's fair to say that Faez's lab is full of amazing, very brilliant students.
I'm lucky to have some good students.
Thank you so much, Faez, for coming on today.
Thank you.
This has really illuminated an entire new vertical of how AI can actually be useful to people. Thank you so much, everyone, for watching, and stay tuned for more monthly episodes about No Math AI.